Hi all, welcome back. In this video, I will be talking about few frequently asked interview questions with respect to Verilog. So as you can see over here on the screen, we'll discuss 6 interview questions. Okay. So first one is a 5 different ways to generate a clock in Verilog. Okay. So what are the different ways we can generate a free running clock in Verilog? Okay. So as you are aware that we can use a forever loop and always. So these two loops are general one. Okay, we are generally using in our test bench for generating a clock. And then by using while loop, do while loop, and for loop, how we can generate a free running clock, I will let you know here. So this is what a simple code for this. Okay, module name is a clock generation. You can give any name. Here I am defining variables clock 1, clock 2, clock 3, clock 4, and clock 5 type of bit. And as you know, the default value of bit data type is 0. The first way is to generate using always block. So always #5 clock is equal to not of clock. Simple one. Another one is by using forever block. So within initial begin block, I'm writing forever #5 clock 2 is equal to not of clock 2. Okay. By using while loop within initial begin block, I'm writing while within parenthesis 1. So this will be like an infinite loop. Okay. And then I'm writing #5 clock 3 is equal to not of clock 3. The next one is by using do while loop. Do, okay, within beginning block, #5 clock 4 is equal to not of clock 4. And just I'm writing while here in the parenthesis. I'm giving the next loop is for loop. Okay. So within initial begin, I'm writing for, and within parenthesis, I'm providing 2 semicolons. So within parenthesis, if we are providing 2 semicolons, it means that this for loop will run infinite times. Okay. And then I'm writing #5 clock 5 is equal to not of clock 5. And in the another initial begin block, just I'm writing a dump file and dump twice in order to see the waveform in our EDF program. And after 500 time unit, I'm just finishing the simulation. It is important because if we are not finishing, it will run for infinite loop and our simulation will have. Okay. So if you just run this code, you will able to see the clock generation. Okay, so as you can see, clock 1, clock 2, clock 3, clock 4, and clock 5. These are the free running clocks. So these are the 5 different ways we can use to generate a clock in Verilog. Now let's see another question. The next question is explain different abstraction levels in Verilog and implement a full adder using 2 half adder. Okay. So for this, I hope you are aware that there are, if you should see the literature, you will find there are 4 different abstraction levels are available. First one is a switch, or we can say a circuit level. Next one is a gate level, abstraction level. Third one is a data flow, and fourth one is a behavioral level. So by these 4 ways, we can implement any circuit in Verilog. Let me explain you each one with simple examples. So if you see switch or circuit level, so here the implementations of our digital circuit will be in terms of transistors or switches, you can say, by using PMOS or NMOS switches, we can design our circuit. And the syntax for this is XMOS. I have written over here. It means X means P or N. Okay. So let's say NMOS or PMOS. Then the instance name, and within parentheses we have to provide first as output, then the control signal, and then the data set. Let's say, for example, if we want to implement a NOT gate using CMOS inverter, okay, using CMOS, how we can implement that? Okay, so as you know, the digital symbol for the NOT gate is this one, right? So whenever we are providing A at the output, we will get the NOT of the complement of that. Okay, so if the input is 0, output will be 1. If the input is 1, output will be 0. This is what the simple NOT gate. So if you want to implement inverter using this PMOS and NMOS, so this is what the simple diagram for this. First we have to connect the PMOS, then below to this NMOS. At this PMOS we are providing VDD as a supply, and at this NMOS we are connecting it to ground. And at the output, if we are joining these two, we will get the output, and we are shorting this input and providing in overall. Now let me explain you the simple Verilog code for this. If you synthesize this code, if you see the schematic view for this particular code, you will find the diagram simple. Okay. Just the PMOS and then followed by NMOS here below to this. Now the code is very simple. Module AIM module. First we are writing input, which is in, and the output is out over here. Right? Then for providing the power supply in ground, we have to use supply 1 for VDD, and supply 0 is for ground. Okay. Here the syntax for this is PMOS, the instance name, and within parentheses we have to provide first is output. So as you can see, output is out, then the control signal is VDD, okay, for this PMOS, and the input is in. Okay. Similarly for NMOS is a keyword, N is an instance, and within parentheses output, okay, you can see output is out over here. The control is a VSS, meaning ground, and the input is in, okay, and AIM module. So this is what a simple Verilog code for implementing a NOT gate using PMOS and NMOS. Okay. If you synthesize this design, you can see the schematic view something like this. The next one is a gate level modeling. So in gate level modeling, there are primitives. Gate level primitives are available that are nothing but the modules that directly we can instantiate in our design and implement whatever we want it. So these primitives are nothing but the built-in in Verilog. Okay. Directly we can use them. What are these built-in gate primitives? NOT, NOT, OR, AND, XOR, NOR, NAND, XNOR, and so on. And the syntax for this is primitive name, then followed by instance name, within parentheses output followed by inputs. Okay, very simple. Let me show you the simple half adder implementation using gate level model. Okay. So if you see the structure of half adder, it is very simple. First is the XOR gate, then AND gate. Okay. And as you can see this box over here, you will find two inputs A and B, and outputs like a sum and carry. Okay. So the code for this gate level modeling is also a module half adder AND module. Inside this we are providing input or logic type A and B, and the output are also logic type sum and carry. I'm using system Verilog for modeling hardware. You can use Verilog also. Then the XOR, okay, this is what the XOR. Then the instance for this is E. You can give any name. Within parentheses we can provide the output. Okay, so you can see output followed by input. So output for this XOR is sum, inputs like A and B. Okay, so sum, comma A, comma B. Similarly for this AND gate, AND is a keyword, A is an instance name within parenthesis, carry. Okay, you have to provide a carry over here, followed by input. So if you see the syntax, correction will be there. So here you have to provide output within parenthesis, carry, followed by A, comma, B. This is not a big mistake. You can correct it, okay? And instance name within parenthesis, the output is carry, followed by inputs A and B. So this is what the gate level model. The next one is the data flow model. So in data flow modeling, just we are using the data manipulating equations. So as you know, the half adder equations, I hope you are aware. Sum is equal to A XOR B, right? And carry is equal to A and B. Very simple. By this diagram also you can write. So half adder, okay, over here. This is what the half adder module and end module. Inputs like A and B, outputs like sum and carry. And here we are using assign statement, okay? Continuous assignment statement. So assign sum is equal to A XOR B, and carry is equal to A and B. Very simple. If you do the synthesis or see the schematic view of this code, you'll find the circuit something. The third one is last one is the behavioral level, okay? Modeling style, okay? So let me correct this. This is fourth one, okay? So in behavioral level, it is like a very high level of abstraction. So here just we are writing the code in terms of behavior of our circuit, okay? It is very high level of abstraction, and generally we are using this behavioral level of abstraction for modeling. So as you know, the inputs and output of the half adder, there are two inputs A and B, outputs like sum and carry. So 4 combination will be possible: 0 0 0 1 1 0 1 1. Okay. Sum, if both are 0 0, sum will be 0, carry will be 0. If input is 0, A is 0, B is 1, sum will be 1, carry will be 0. If A is 1, B is 0, sum will be 1, carry will be 0. And at the last one, both are 1 1, A and B, sum will be 0 and carry will be 1. So by following this truth table, we can write the code for this half adder. Okay, so over here you can find the module and A module. We are defining the inputs and outputs A, B, sum and carry. Within procedural block, we are already using the case statements over here. Okay, so case within parenthesis, curly braces, the inputs A and B. If inputs are 0 0, sum will be 0, carry will be 0. 0 1, sum will be 1, carry will be 0. 1 0, sum will be 1, carry will be 0. 1 1, sum will be 0, carry will be 1. Okay. So by following this truth table, we can write the code, and it is very high level of abstraction for writing the Verilog code. Okay. And if you do the synthesis for this, see the schematic view, you will find the circuit something like this. So you can cross check also here. Let's say, for example, if you see this sum expression, sum is equal to you can see over here the select line is A and B. Okay, so if we verify, let's say A bar B bar, this is what is 0, right? Into 0 plus 0 1, right? So A bar B into 1 plus 1 0 means A B bar into 1 plus 1 1. Okay? So A B into 0. Okay? This is what is 0. 0, anything multiplied with 0 is 0, right? So it is A bar B plus A B bar. This is nothing but A XOR B. This is what is sum expression for half adder, right? Similarly, if you verify over here, A bar B bar, okay, This is what is select line and 0, right? So A bar B bar into 0 plus A bar B into 0 plus A B bar into 0 plus A B. Okay, this 3, right? A B into 1. Anything will, if we are mentioned 0 is 0, and this is what the A B. This is what the carry expression for half. So if you synthesize this code, we say the schematic way, we'll find the output something like this. So this is what the simple, different abstraction levels of in Verilog. Now let me explain you that question, how we can write the full header by using two half header. So if you see the top level diagram over here, in this black box, you will find inputs like A, B, and C, and output is sum and carry. Okay. And here we have to use two half header. Okay, H1 and H2, you can see over here. So let me show you. These are the two half header. Okay, already we written half header code. Okay, I will show you the code also. So A, B, and C are the inputs, and sum and carry are the outputs. Okay. If we connect the half header here, okay, A and B, if we are connecting to this, and sum we are providing this to another half header input A, and B if we are taking it from C, and then if we are connecting one OR gate over here, okay, and the sum of first half header if we are connecting to this OR gate, and the carry of half header 2 if we are connecting this OR gate, okay, here we'll get the carry, and this sum will get from the sum of this half header. This is very simple. Okay, let me explain you with the help of code so that you will easily understand. And this internal signals we have to define, like this carry which is going to this OR gate is L1. This sum of first half header which is we are connecting to this OR gate, it is I2. Okay, this is I2, right? And this is what the I1 sum of this first half header to the input to this half header 2. This is L1, this is L2, and this is what the L3. The internal signals we have to define. In case of Verilog, we have to define using while. In case of system Verilog, we can use logic. So this is what the simple full header by using two half header circuit. Let me show you the code for this so that you will easily understand. So here if you see the code, okay, so first we have to write the half header code, right? So we can use the data flow modeling style, like half header, inputs and outputs, inputs like A and B, and some outputs like a sum and carry, and we are using assign sum is equal to X for B and carry is equal to A and B. Okay. Now inside a full header code, we have to make an instance of this two half header, right? So the top level diagram, if you see, A, B, C in, and outputs like sum and carry, right? So A, B, C in, and output like sum and carry. Okay. Then we have to instantiate these two half header over here. Okay. First, we have to define the internal signals like logic. In system Verilog, you can use logic I1, I2, and I3. Okay. Then first half header. Okay, this is what the name of this half header module. The same we have to reuse over here, half header. The instance for this H1. Okay, and within parenthesis we have to provide the signal names. Okay, so for this half header, inputs like A, B, and outputs like this I1 and I2. Okay, so over here you can see I1 and I2. For this another instance of half header H2, within parenthesis we have to provide inputs like this L1, then the C in, and the output is sum and I3. Okay, so as you can see over here, I1, C in, sum, and I3. Similarly for OR, there is one OR gate, right? The inputs for OR gate is I2 and I3, and output is a carry. Okay, and OR is a keyword too, so OR the instance for this, within parenthesis we have to provide outputs followed by inputs. So output is a carry, okay, followed by inputs like I2 and I3, right? And this is for the AND model. If you write a test bench for the simple test bench, or declare the input and output over here, okay, and this design instantiation in system Verilog, just in within this initial begin, I'm saying input to be 0, and I'm using one for loop to generate the stimulus and providing this stimulus to input A, B, and C. Within another initial begin block, I'm printing the values of all the inputs and outputs, and just one dump file and dump wires in order to see the waveform. If you run this code, you will find the output something like this. Let me run this code and we'll analyze the output. Okay. Later you can analyze the waveform. Okay. I will not explain you waveform, you can analyze. Just let me show you the console result. So this is what the output. Okay. So let me explain you the output first here. So if you see the truth table, when A, B, C are 0, 0, all 0, sum will be 0, carry will be 0. 0, 0, 1, sum will be 1, carry will be 0. 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, okay, and so on. So the simple one is like, if you want to analyze the output, sum will be sum of 1. If you see summation of 1, sum will be like, let me take the pen over here. So summation of M, if you see, for this is 1, 2, 4, 7. Okay. We mark here 0, 1, 2, 3, 4, 5, 6, 7. So for sum expression, summation of M will be 1, 2, 4, 7. Similarly for carry, it is like 3, 5, 6, 7. This is what the truth table. If you analyze the output I have taken over here from the PDF program. So if you see, sum will be like 1, 2, 4, and 7. Similarly, carry will be 3, 5, 6, 7. If you see, if you compare these two, you find the same result. So this is what the simple way how we can implement the full adder by using two half adder. Okay. The next two questions, there are few other questions are also. What are those? Let me see one. Verilog code for passage detector, then implementing the latch using 2 cross 1, and Verilog code for frequency divide by 2. We'll see in the next video. Okay. So here in this particular video, we discuss 5 different ways of generating a clock in Verilog, and what are the different abstraction levels available in Verilog for modeling hardware, and implement a full adder by using 2 half. So with this, I hope you have understood this concept. If you have any question, you can put your questions in the comment box. We'll discuss those questions. Okay, before this, discussing the next question, I already explained the passage detector. I request you to first go through those videos, particularly that passage detector video, and then we'll try to write a Verilog code. We'll see the schematic view also. Okay, so with this, I hope you have understood these 2 questions, and also I hope you enjoyed this video. So thanks for watching this video. Thank you.